So today we are going to look at vector operations and unit vectors, and we're going to look at them two different ways. Visually, so it's referred to as like geometrically when you have the actual vector there, and then we'll also look at it numerically and algebraically. All right, so along with vectors come scalars. All right, so a vector can be multiplied by, and it has to be a real number, and it's a lowercase k that represents a scalar. All right, and it's called a scalar. This will change the magnitude. What's the magnitude of a vector? The length of it, or the size or length, okay, or the distance, or depending on whatever you're using there. So the magnitude is the size, and if k, our scalar, is negative, then the vector will reverse to the opposite direction. So this over here shows us a few different variations of what scalars can do to v. So here's our vector v. Then this is 2 times v, so it's going in the same direction, but it's twice the length. Here's half of v, and then this is negative v. All it did was just flip it around the other way. Make sense? Easy enough? All right. So then a geometric representation of the addition of vectors is over here. So we have v and w. The vectors are positioned so that the tip of v coincides with the tail of w. Okay, so this is what it's called, and what you end up getting is a resultant, and it extends from the tail of v to the tip of w. So here's v, where v ends, w begins, then this right here is your resultant vectors, and we're going to be doing some stuff with resultant vectors eventually. The difference of the two, so if you're going to subtract, so I have v minus w. You can also write it as v plus negative w, because that's what's happening here. V is still just v, but instead of w coming off of it this way so that we get that resultant, it's going this way because it just flipped around, so then this is v minus w. That's the resultant vector there. Okay, so it's the same. If you've ever heard the phrase from tip to tail, it's the tip to tail version or model. Okay, we good on that? Easy enough visually? All right, so now we're going to look at what happens algebraically. So if we have vector v, a little arrow there, and these are bold, but I'm still going to put arrows on top of them. And we have a1, b1, and then we have w that is a2, b2, because they could be just anything. So remember that k is our scalar, and it's a real number, so then if I have k times v, that's going to equal, so v is a1, b1, this will be k times a1, comma, k times b1. It's that easy. You literally just multiply both of the numbers. If I'm going to add them, v plus w, then that would give me a1 plus a2, comma, b1 plus b2. Then if I'm going to subtract them, it's just what you would think it would be, and that's going to be a1 minus a2, comma, b1 minus b2. So the adding, subtracting, multiplying by a scalar, all that stuff is super easy and just like what you would think you would do with it, okay? Just like what you would do with ordered pairs. All right, so we're going to find each of the following. We have A, B, and C here. So to do 2 times vector C, I would have 2C equals 2 times negative 4, and then 2 times 5. So that 2 times C equals negative 8, 10. Okay. So that would still be going in the same direction. It's just going to be twice as long. Easy enough? All right, so then we have C minus B. So C, vector C minus vector B would be C, negative 4 minus 1, comma, 5 minus 7. So that's C minus B equals negative 5, negative 2. Any questions? It really is that easy. It's no trick. And that's sometimes what you think of it. right, so then I have a minus 3c. So a minus 3c equals, so a is negative 6 minus 3 times negative 4, and then 2 minus 3 times 5. So that a minus 3c will equal, so that'll be negative 6 plus 12, so that's positive 6, and then 2 minus 15 will be a negative 13. Any questions about that? All right, so add a fraction bar that disappeared here, and then you do number 4. Got negative 4, negative 6. Any questions about that? All good? All right, so let's talk about unit vectors. All right, so the standard unit vectors, I and j, are positioned along the x and y axis as are defined as, so here this point is 1, 0, this is 0, 1. So just like we have a unit circle and the radius is 1, this is 1 unit, our unit vectors have a length of 1. And we have one that represents the x unit and one that represents the y. So I goes with x, j goes with y. And they can be, so these are bolded, but there's a couple different ways that you can represent the unit vectors. They can be bolded like all the other vectors. We could have arrows over them like all the other vectors. Or a third way, and the way you would see, there's a lot of engineering and physics applications, you'll see this, but I don't think that's how y'all are doing it in physics because you can, like I said, there's different ways that all means the same thing. You put the little hats over them. So it looks like a little rooftop. So they're actually referred to as I hat and j hat, but they're all the unit, that all means the same thing if we use I and j. I think it's just to distinguish between it just being a regular vector, but you can't put the little hats on every vector. It only works for I and j, okay? So since this is 1, 0, that vector is going to also be 1, 0, but we're using those pointy brackets. And then this is 0, 1. Okay. So it says any vector v that is written as AB, right? So this is component form. This right here, it's what we did yesterday. That is called component form. It's important that you know the different names so that when you're asked to put it in a certain form, you know which one it's asking you for. So this one's called component form because you have an x component and a y component, right? And then we could write this as vector v could also be a times I hat plus b times j hat. This is called a linear combination. You're adding them, it looks like a linear equation. So we have component form and a linear combination form, okay, of vectors I and j. So we're gonna do this right here to show why this is exactly the same thing, okay? So we're gonna rewrite AB as a sum of two vectors. So I'm gonna say, okay, vector V is equal to, I could say this is A comma 0 plus 0 comma B. So what you know about adding vectors, would you agree that that's this, if I add those two together, I get vector A comma B, right? Okay. So now I'm going to factor A and B out of each one of these and make it a scalar. So I'll get A times 1 comma 0 plus B times 0 comma 1. Because if I were to multiply it back and I multiply a times 1 and a times 0, I'm going to get those back, right? Everybody okay with that? And then we've already defined this is I and this is j, so that means that vector v is a times I hat plus b times j hat. So that's why that's just another form. And which form you actually use when you apply it depends on what you're doing with it. So right now we're just kind of learning the forms and we're going to do what we're told and which ones. But when you actually start to get deeper into vectors and apply them, you have the different forms for different reasons. Okay? You're not going to have to decide which form to use at this point. You're going to be told, do this, do that. Okay, and then we'll get there. All right, so we're going to rewrite these as a linear combination of I and j. So, and I'll do it a couple of different ways, so just, it doesn't matter. So vector v can be 2 times, we'll do the hats first, I hat plus 5 times j hat. So vector n, we could say is negative, no more brackets there. Negative 7 times I plus 3 times j. And I'll put the little vectors over them because it's the same either way. I just want you to at least know that I hat and j hat are a thing in case you see it in, anywhere else and you're expected to know what it is. Easy enough? We're good? Okay, so 3 we're doing the same thing, but in order to get it in the linear combination form, I have to know the component form. We know how to get component form from this because this is what we did yesterday. So I have vector rs, that's going to be, remember it's x2 minus x1, so I have negative 5 minus a negative 9, so that's a positive 4. And then negative 6 minus 8, that's a negative 14. Everybody okay with that? So then that means, so that's my component form, and this is my linear combination form, 4 times I hat minus 14 j hat. I kind of like the little hats better than the arrows. Questions? And you do number 4. What questions do you have? Anything? Yes, sir. Because you could do it either way, so I just did one way and one the other way. I don't really care how you do it. Because I want you to know that it's the same either way. But remember that I could, even though I can put the hats on I and j, I could not put a hat on v. Because that's not it's for the unit vectors. Okay. So either way, it doesn't matter. I'm okay with either way. We good? All right, so your assignment is in Delta Math. Make good use of your time and get on it.